So there's a couple of things we need. So I'm not going to finish these slides today, but there's a couple slides we need about homework. So I'm going to go through those. So that's and then 16. So yeah, so we're dealing with a eutectic phase diagram in the homework, and this just shows. So each of the, so like I said before, like you can make these phase diagrams by this is here. Basically, so you have the Hildebrand equation, this kind of U-shaped thing for the free energy. And then if you have two phases present, you have two of those Hildebrand curves, and the lowest free energy is the phase that it will become. Like it'll become a liquid in the middle, and then like there's a transition point. Right. So basically, if you draw a line across this where a tangent meets the two curves, those are the phases that are in equilibrium because they have the same chemical potential, which would be like the derivative of that for the moles of this, whatever the component is here. And so that gives you these like phase equilibria. Right, so when you get to the eutectic, which looks like something you couldn't really make that way. So you have like three phases here, like you have two crystallographic phases and you have a liquid. And in this case, there's a third crystallographic phase. So each of them has a Hildebrand equation. Or is it x plus ln x term, and then a x and the interaction parameter thing. And so basically, those curves shift with temperature in different ways. And they can be symmetric or asymmetric, depending on, so you can put in different terms into the enthalpic term and make them change. But so basically, this just goes through the for a eutectic, like how that would work. So you have like T1, so liquid is below all those solid phases. So it's got the lowest free energy, so it's a liquid all across T1, across the whole composition. At T2, you form this crystalline phase, the magnesium oxide phase. So magnesium oxide has a lower free energy than the liquid. And there's a tangent for the two, which means you have a liquid solid equilibrium region. We have both phases present. There's a tie line between those two. So if you land at some point in this, that would be mostly magnesium oxide and a little bit of liquid. So if you have liquid domains within magnesium oxide, once you get to 50%, then it's a 50-50 mixture. Once you get to have more liquid, so the tie line, like you take the distance from the composition where you are over to that phase equilibrium line, and then the total distance, the ratio of those two gives you the fraction of liquid in the material, and the composition of the liquid phase is given by that point. Right, so you need to know how to do that basically for the homework. Be able to, if you can't get the percentages, you can't draw a cartoon of what the phase is, or what the structure is. In other words, if you're over here, it's going to be mostly liquid. So these crystals of magnesium oxide will just precipitate out. So liquid phase, you have a minor component of the solid, it'll nucleate and just fall out of solution. So you get like a powder at the bottom. Right? And if you're over here, your majority is solid and the liquid is just droplets. It doesn't fall out because the matrix is a solid. Right? So you should be able to draw a cartoon of what you'd expect to see in a micrograph of this stuff. In other words, liquid droplets in a solid, or like solid that precipitated out at the bottom. Right. And that anyway, so you get to T3, then you have the three phases. So the two crystal phases and the liquid phase. So liquid phase in the middle of T3, liquid, let's see, this is T3, so liquid dominates there. We have two of these tangent lines that match up. So you have two equilibria. This is where you take it all magnesium oxide. That side you get all yttria oxide. Right, so T3, and there's two crystallographic forms, as a hexagonal and a cubic form for the yttria oxide. So basically, those two are going to show up as two kind of parts of the phase diagram here. There's a cubic It's the hexagonal is over here, this little thing. Then the hexagonal, so there's also, you can't see it in this thing, but there's also a line, the equilibrium line between the hexagonal and the crystal. So those two would also have two phases in equilibria, which gives rise to this little nib here. A lot of times when you're, I mean, if you're doing metallurgical crystallography, you're looking for those little regions to get some magic property, like super alloy strength or something. And so basically, those little nibs are important. So people will spend their whole career on just that nib, the phase diagram, to try to get to it to make some special property. I mean, in this case, I think these are superconductors, so might have special properties in there. That's why, otherwise, people normally would ignore something like that, like some other phase that shows up. So if it's there, it's because somebody studied it. Then if you get to, so that's like T3, and then if you get to T4, then you just have magnesium oxide, nitric oxide, and the hexagonal form in equilibria, and there's no liquid. So liquid for T4, so this and that are in equilibria, and there's no point where the liquid has a lower, even though it looks like it does, but basically the liquid would be above, usually above that dashed line. They have the two phases at equilibria. I guess is T4 right at the eutectic? No. This looks like just at the eutectic because you have the three phases in equilibrium, liquid and the two solids. So T5, I guess, oh, T4 is that line, T5 is the bottom line. This is the eutectic point. We have three phases. So the tangent crosses three phases. Then T5, you just have the two solids. That was what I was talking about. So basically, magnesium oxide and the hexagonal yttrium oxide. Right, so it's possible to have, and then you can do the same kind of calculations like I showed before with the chemical potential thing to calculate that phase diagram. So you can calculate the whole eutectic phase diagram. And things are even more complicated by using these activity coefficient, and then that reduces back that you end up with just the heat of fusion and the melting point for the components. And so even though it seems like impossible, it's possible to calculate the whole phase diagram if you know those like melting points and enthalpies. And it seems like not that you couldn't really do that, but you can. So that's one thing. So I mean, we'll see a eutectic phase diagram. That's why I mentioned this one. And funny, the rest I'll go over on Tuesday, I guess, but unless we have time today. But 26 is so then there's this other thing, like a monkey wrench thrown into the whole thing. So sometimes there's a mixture of things that's absolutely perfect. So that you're mixing calcium oxide and zirconia together, and you're getting different phases like zirconia, calcium oxide. And then basically there's a magic composition, CaZrO3, that's just stoichiometrically perfect. So that, because that's so perfect, it has a really low free energy. So when you get to that composition, you just make that one thing. It's that almost acts like, it's almost like you split the phase diagram into two parts around that. So this becomes like a pure phase, more or less, right? But it only exists at that one composition. Okay, so otherwise, if you deviate from that, then you have a tangent that goes from that point over to the other Hildebrand equation for the zirconia. Then you'll have the zirconia and you'll have that phase in equilibria. So you have a tie line between those two. So that this would be, I guess, oh, this blue line is where that is, right? So you have a zirconia phase over here. Let's see, at about 0.2. So that would be like this phase. The CSZ is this zirconia phase, and that's in equilibrium with the intermediate phase, right? So you have a tie line, even though it doesn't exactly look like a tie line because this is a straight single composition. There's a tie line between those two. So if you go over here, then you're going to have a sea of zirconia with a little bit of the intermediate dispersed in it, like 20%. If you go over here, you have an intermediate phase with some of the zirconia domains in it. See, this is what you have to be able to do, is to say like, I'm gonna drop down to that temperature. And then then at that temperature and that composition, then I take a micrograph and I get little domains inside a C. So what's the C and what's the domains? And then what's the composition of the C and what's the composition of the domains? So the compositions you get from these points on the ends of the tile line. So that composition of them, if you're here, if you're at 0.25 or something, you're gonna get majority zirconia, and so in the number of those dots is going to be like 25% domains of this intermediate phase, and the intermediate phase is a fixed composition, and the zirconia phase is going to be a mixture in composition of zirconia, but it's going to be a partial calcium oxide and zirconia mixed, right, with the composition of that equilibrium phase. I guess here they're not showing all these other phases, so it can get complicated, but basically each of the other phases is going to just be another Helmholtz equation here, another U, and you're going to have there'll be a tangent line between the zirconia and this TSZ phase, and then you'll get those two positions, those two equilibrium phases, and then the calcium oxide is in equilibrium with the intermediate phase, because it's a straight line. So it's basically that composition calcium oxide, and then that intermediate phase is a fixed composition. And so the tie line goes with that, and then that you pick out that intermediate phase is that point, or at this point, the blue line. Right, so anyway, intermediate phase kind of throws a monkey wrench into the thing, so you have to kind of, anyway, it happens quite a bit. So basically we'll see it in our, I think that's all I wanted to go through for that. I mean, any questions on that stuff? It's complicated, but you have to just, if you had materials science before, then this stuff is like the whole course. The whole course is just like this chapter. If you haven't, you just have to sort through. It might help that if you've had like chemical engineering, thermodynamics, you're really familiar with these phase diagrams, right? The azeotrope phase diagrams, like the main one, and then you can kind of link it back to everybody did that. I mean, they're the same kind of phase diagrams, right? So anyway, so anyway, hopefully you can just sort through this, but kind of get a feel for it, and then right. So there's that business. I'm gonna quit that. Quit this thing and go over to the homework, which is, so it's about batteries. So batteries is a pretty interesting topic these days. People are interested in it. And so this linked up, so lithium ion batteries, like the main one people are interested in right now. That's like the workhorse of everything. Basically, it's going to have like graphite. There's an anode and a cathode, and there's a separator membrane, and there's a lithium fluoride salt solution, liquid that's an electrolyte in this thing. And then you have some kind of cobalt, nickel cobalt alloy for the cathode. Right. So you have these two. So when you're charging, you kind of charge up the anode, and then when you deplete, it goes into the cathode. Right. The lithium ions migrate to the cathode, and that kind of is how you generate energy. So you think like, so there's people working on basically the anode and the cathode is like the main topic of interest. Like, how do you make it better? Right. So one way, so the way both of these work is that they're kind of layered structures, and lithium ions kind of fit in. And the cathode, it's an alloying process. So you have a mixture of metals, you make a lithium alloy. So lithium goes in as an alloying process. In the anode, the graphite is just sheets of carbon. So it's like basically lithium can fit into the gallery between the two sheets of carbon. So kind of like graphene sheets, and the lithium ion can fit in there. Right. So the game is the reason why you're using lithium is because it's got the lowest density, right? And then it's got a pretty good potential, electric potential too. So the game is to fit more lithiums in. And you can do that so silicon will make an alloy with lithium. they can hold like 10 times as much per weight of silicon. So silicon's also a light metal. It's like aluminum kind of. Basically, it'll hold about 10 times as much as graphite because it associates, because the density is lower than carbon. And it also, I mean, the specific amount of lithium it can hold is 10 times as much because its weight is lower, and also because it coordinates 6 lithium ions per silicon atom, whereas carbon just kind of takes 1. So basically you end up with 10 times improvement. There's problems with lithium, and there's a bunch of problems with it too, but right now, like for a car battery, it's going to have graphite and it's going to have little particles of silicon put into it, silicon metal. And then they're trying to make this all silicon if they can. And even better than silicon is lithium because it weighs less. So basically, you can make this with lithium or silicon or graphite. Graphite's the worst of the 3. That's the current one that dominates the batteries. And then graphite mixed with silicon's the next stage. Then pure silicon's probably the next battery. So you can imagine this part of the battery, you can easily get 10 times the capacity that you have right now, which would mean like basically charge, if it was an electric car, you'd charge it once a month for the same mass. So it'd be like changing the oil, and you never have to charge it, right? But the problem is you need 10 times on the cathode too. So whatever this dumps, it has to go somewhere. It goes into the cathode, right? So you could do that by making the cathodes 10 times bigger. That's kind of what's possible to do. Or you can kind of mess around with the composition of the cathode material. And the cathodes are just these alloys, right? So basically manganese and cobalt and nickel. And those are all like metals that come from the Congo, in short. So the cobalt particularly is supposedly half of it is mined by little barefoot kids that are kind of slaves, more or less. But I mean, there is some like debate about that. So, but basically that's the theme of a lot of people right now. There are also huge mines in Zambia and in the Congo. So it's in the southern part of the Congo, DRC, and then in northern Zambia is where there's actually big companies with giant mines. And then there's also these artisanal mines with little kids. So anyway, so this paper is about using cobalt and like how you make it better. And so anyway, so that these cobalt alloys, right? So they list the alloys they're looking at here someplace. So it's manganese, lithium, manganese, or nickel alloys. Let's see. And then there's going to be this lithium F compound electrolyte that's in the thing. So basically, lithium. That's the thing that kind of blows up. Like lithium's flammable. Like it'll ignite itself. Right. So that's one of the main problems with it. I mean, it's like basically silicon. Any of the metals will like burn. Right? Don't want to make an oxide, so they just will leave there. And you feel them with the ground state metals. So basically, it's ready to blow at any time. Any of these metals. So anyway, so it has to be kept away from oxygen mostly. But so anyway, so this is kind of a processing. See, I'd like to download this thing, so I should have done. See, how do I do that? Translate, okay, how do I do that? Or how big can I make this? I can make it pretty big here. All right, that's good. So we're kind of interested in this phase diagram. So, and this is a phase diagram for lithium hydroxide and lithium nitrate. So it's pure lithium nitrate on this side, and it's pure lithium hydroxide on this side. So this isn't the material that's used as the electrolyte, which is a fluorolithium compound. And then it's not the material that's used as a cathode or the anode either. So this is just something that they add to it that has lithium in it, right? So, which is good, because you're gonna end up with lithium in the cathode anyway at the end after. So you go through like the first cycle, the crystals kind of get melted by the lithium fluoride electrolyte, so it breaks them apart. And then, so you go, as you go through the battery cycles, you want to cycle the batteries, and they do that in here. The first cycle, you lose a lot of lithium, it goes into the battery and gets permanently, goes into the anode and cathode and kind of gets permanently stored there initially. So your capacity drops immediately when you first start charging. Cycle retention is what, so you're automatically going to lose some because you have to break up the crystals, and the lithium has to go into the crystals. So there's some drop, and then, but ideally you want to have it drop initially and then go flat. That's kind of the ideal cycling for these things. You can see they're going like 200 charge cycles. So that's like an experimental. In a real use, you're going to go like hundreds of thousands of charge cycles. So they're just looking at the beginning part where you see the most kind of degradation of the thing. So they do the actual battery studies in this paper at the end, but we're not really looking at that part. Anyway, what they claim, so let's see, the initial material that they're looking at, let's see, they list it here someplace. Here, this is the material they're looking at, right? So the LMR is this lithium, manganese, nickel, cobalt oxide. That's a cathode. And there's another cathode. So this is like a research cathode, and there's another cathode. It's more like an applied cathode that we look at later on. Basically, this is the one we're kind of interested mostly in. So it's a weird combination, odd combination of, so these are all transition metals, and they can more or less like swap with each other within the lithium oxide salt thing, lithium oxide alloy. Right, so it doesn't matter that you have perfect stoichiometry in this. Right, so because they can exchange for each other, and they find a composition that works the best for the battery, essentially, right? So anyway, so there is a paper that talks about, this paper just talks about how you build a battery, like what the structure of it is, you know. I mean, it's not really a paper, it's like a website. And then there's a couple review papers in here if you want to read it, you know, you don't have to. Lithium manganese based layered oxide cathodes for lithium ion batteries. So both the cathode and the anode are these layered structures where the lithium can kind of fit in. And the silicon also ends up kind of being a layered structure. So it accommodates the lithium ion by kind of layering this diamond cubic structure. So the other thing about swapping out, so that each of these different materials for the cathodes and the anodes have different electrochemical potentials. And it turns out graphite has a relatively low electrochemical potential. So you also get a boost using silicon and lithium, but the electrochemical potential is like 3 times higher. So per lithium ion that goes in, you get 3 times the juice out of it. There's various things people are playing around with in the compositions. There's definitely better things than what we're using right now. Anyway, this paper goes through, I mean, I think it's interesting to read about, but basically, and I think you're going to see more and more about this battery things, and lithium ion is actually a good thing to start with because the technology to manufacture these on huge scales like already exists. And every other kind of battery that you're talking about to substitute for this, you'd have to start from ground zero and build factories to make it. But if you can just have a substitute anode or substitute cathode material that goes in, you're good to go in like a year. You know, but if you want to start with a new battery, you're talking about like 15 years from now. Right, so basically we're a little bit stuck with lithium batteries. I mean, anyway, so you can kind of look at that too if you want. This paper is just about like the technology of batteries. I think it's interesting, but if you're not interested, you don't have to look at those. Anyway, so the point of this is that they're going to do this. They show a cartoon what they're doing. It's a Nature paper, so it's got to be a cartoon. So they start with this crystal. So that they're going to usually put this in a slurry process to make the cathodes. You start with these salts. You just have all those materials, and you kind of mill them together. And then you gotta put it in a slurry and make these particles from it. So we show pictures of the particles here somewhere, so not those particles. Might be in a supplement here. Oops. It's in an awkward place. Yeah. The supplemental, let's see, it's definitely a picture that I'm looking for here. Those are those things. I'm looking for the comparison of the two. It must be in the paper. One of them looks like Mars here. There. Looks like an asteroid or something. That's a bad one. This is a good one. So the bad one is made up of all little grains of this alloy. Basically, when the battery's running, it's gonna take lithium in, let the lithium out, and that process is gonna break apart all those things and makes new surface. At the surface of it, it forms what they call a rock salt phase, which is like an NaCl phase, like FCC crystal with a so it's basically FCC, like sodium chloride is like this thing. So it's did that work? It's trying to. I don't know why it zooms in whenever you start it. Like, why is that the natural position for it? I think it would be something like that, but anyway, then the CLs that go here. That's like rock salt, and then do that in 3D somehow. Like Na here, Cl here. So you could write it, so I could swap the Na and the Cl in it. I think, in other words, if I made it like Cl, Na, I'd get the same structure. That would be the same. It's just like I shifted over just one, right? So anyway, so that's a rock salt structure, FCC. And these that weird alloy thing can make a rock salt structure, and that's a non-active phase. So all these anode cathode things are going to have something detrimental, and usually it forms at the interface. So you don't want to have rock salt of that weird lithium oxide thing. If you get that, it kills the battery, right? And if you have, every time you break one of these little pieces out of that, it forms that phase on the surface of it. So the more this thing breaks apart, the more of that phase you get, and the more the battery decays. You're losing lithium every time it makes a rock salt. The lithium's gone from that, so you're losing capacity of the battery when you do this thing. So the game is to not lose capacity from the battery if you can help it. So let me fix this thing. Oh, it is okay. Anyway, so the way to get around that is they take these things and they put it into a thinky mixer, which is a plenary mixer. So you see these kind of mixers around. There's also spin-offs on the thinky mixer. It's got a cup that spins in a circle, and that cup spinning in the circle wings around in an arc, right? So it's like total mixing. They claim that you can mix anything this way, like it's like super mixer. So they're using that. I mean, you just buy them. I think they're like they're I don't know, 10 grand or 15 grand to buy one. Yeah. Oh, sorry. Yeah. Thanks. Oops. PC project. Yeah. Sorry about that. That's weird. I can see it. I'm fine. Anyway, this is just a schematic. You can just look at Slinky Mixer. I could even spell wrong, it'll find it, I think. Images, it's a thing like that. It's got to see it's tilted a little bit, and that thing goes 6,000 RPM. It's like pretty fast. And it basically will rip everything apart. So there's a lot of energies going into it. So anyway, so they show like what starts, and this is the bad one that's going to break apart into pieces, and every time it breaks apart, it's going to form that rock salt on the surface, which depletes of the active material, makes it a bad cathode. Eventually, that's a decay process. So they say like somehow they're going to put in magic foo-foo dust, lithium hydroxide, lithium nitrate, somehow it's going to go in and like rip these things apart. And then when those things are ripped apart, they later are going to anneal this thing. The calcination means you stick it in an oven for a while and it cooks. So you're kind of like baking it. And it'll grow from these little teeny crystals into these giant crystals that are all good stuff. And there's only a little bit of bad stuff at the surface. And in fact, the bad stuff, this rock salt phase at the surface, is actually like much thinner in that case than it is over here. Like they find that also from TEM micrographs. Right. So they say, right, so this is like MIT or something. Otherwise, this would never be in nature, I think. It's kind of weird because it's just a processing technique. These guys are like nuclear engineering, MIT, and then like Ulsan National Institute. I don't know where that is. Oh, here, Korea. Okay. And then State Lab, China, and then MIT, Material Science. So they're like MIT, basically. I don't think the Ulsan thing is like great. And China's good, but school, it's like the state key laboratory is probably pretty good, I guess. Anyway. Right, so kind of by name, they get this thing in nature because it's just a processing thing. So it's not really, maybe it could make the batteries better, but what they show is that it goes from 86% to 92%. So that even the gain they get from this isn't so huge. It isn't like a 10-time gain in batteries. So it doesn't seem to merit the publication that they have. But anyways, for us, it's good because if you learn a little bit about batteries, that would be really useful, I think, in the long term for your career, you know, because this kind of thing, because a lot of jobs in this. So if you can just figure out a little bit of it, it would help. So anyway, just get a kind of a feel for kind of what a battery is, lithium ion, how it's put together, and what people are studying. You know, that's the point. So they mix it, they put in a thingy, they mix it for 3 minutes, they get that. So it starts as this, just the components that they put in. Then they get this after 3 minutes, 6 minutes they get that, and 12 minutes they get this. Then the thing they get after 12 minutes is these big crystals that are like good, better, theoretically better for the cathode than the thing they started with. So how does that work? Well, they take this lithium and lithium hydroxide and lithium nitrate phase diagram, and it's a eutectic phase diagram, kind of. Okay, so it's got a little twist to it. That's why I wanted this to blow up, because you can't really see it unless you blow it up. So it's got a eutectic point right here. So that's like the low melting point is eutectic. So they have a two solid phases in equilibria with a liquid phase. The liquid phase is the white. The two solid phases are this intermediate phase. So there's an intermediate phase here, this straight up and down line, but the intermediate phase only exists from like that point to that point in temperature. Right? So it's kind of, so intermediate phases can exist only in a certain realm of temperature sometimes. Sometimes they go all the way through, but this one only exists there. Once you get below that, then you separate into the lithium nitrate and lithium hydroxides. The nitrate's on the right, hydroxide's on the left. So those are just a pure, this is at 100 degrees C. So
what is the difference between the right side of the immediate, what is it?
Like the green and the blue?
Yeah.
Yeah, so you got, so this intermediate, think of it as if it's another line, like this line of the phase diagram. Like in other words, it's at 0% of something. It's at pure, this is pure nitrate, lithium nitrate, right? Well, this is pure intermediate. So it's like as if you had another line here just plopped in there, because this is a perfect thing, just like that's a perfect thing.
So for 0.5 mole, if we decrease the temperature, so it will go from lithium hydroxide solid plus liquid to direct in the purple region.
No, yeah, I mean, if it depends what temperature. If you go to this temperature, you form 100% intermediate phase, intermetallic. So you make 100% this thing. If you drop it 50% and you go right there, you get exactly this composition. That's the stone crystal.
Yeah, so we'll get into direct this purple region from the top region.
Yeah. So if you quench down to here, you just get that. That's all. You just get that. If you quench down to here, you get 50% lithium nitrate in lithium hydroxide, so it's going to be grainy, and it'll be half and half. If you see the micrograph, it'll just be a bunch of grains. Half of them will be lithium hydroxide, they'll have to be lithium nitrate. Pure, like pure phases.
But if we stay in like in homework, it has said that in 175 degree.
Yeah.
So it will be in that line.
Right, then you make just that phase. If you quench there, you make just that phase. You just make that one perfect phase.
So it would be just Li2OH NO3.
Yeah, and that's a
in
crystal. Yeah, that's got its own crystal form, and that's like a perfect thing. So it's just permanently that one thing. Yeah, it can be confusing, right? So that's why, so your processing is gonna, so this is like a guide to processing. Say you wanted 50-50 mixer lithium nitrate, lithium hydroxide, well, you can get it, but you have to quench fast and go to this point. Quickly throw it in a bucket of whatever you need to get to 100, like water. You throw it in a bucket of water, you just get that and that. If you want to get this, you're gonna have to put it in something a little more special, like an oil bath that'll go to like 175, and you can get just the intermediate phase. If you quench that down, that's solid. It's not going to decompose into those two things. Like it's just going to be that. So if you take that after setting at 175 and then quench it, then you'll just have the intermediate. So you can get it kinetically by locking it in. Even though when you're down at room temperature, these two phases are in equilibrium, but they aren't there. If you have this perfect salt mixture there. Right. So the interesting thing is if you come down here and then you like do a slow cool, so you're not quenching anything, you're just cooling down. So what happens? Well, you make pure lithium hydroxide and liquid, and that's just going to precipitate out, right? Because it's going to be like, so it's going to be like a little bit of, see, it's just a little distance from that dashed line to this line, right? So it's only making like 2% lithium hydroxide, and it's all liquid otherwise. So that stuff's just going to fall out, maybe so it could settle to the bottom. So it's extracted. I mean, conceivably, right? So until you get to, so then the liquid phase composition, which is this black line, the liquidus, right? So you just follow that down until you get to here. And then that's the liquid you start with, because all the other lithium hydroxide has been pulled out. You already pulled that out by slow cooling. So you have a new composition for your liquid. It's here. And there's little particles of lithium hydroxide at the bottom. Maybe, they're extracted out. So once you have that composition, then you slow cool some more. And then all of a sudden, you're at almost a 50-50 mixture of liquid and the intermediate phase. So you're going to start making this intermediate phase. But so at the beginning, it's almost like 50-50. There's a little bit more intermediate than there is liquid. But as you go down, you get more and more intermediate and less liquid until there's no liquid, right? So basically, you're going to have, by the time you get kind of a lower end of that little teeny gap, you're going to have like a matrix of intermediate with liquid droplets in it that have the composition, the eutectic composition. So within those liquid droplets, you're going to get, in this region, you're going to get eutectic decomposition. You get that tiger skin thing. You get like a tiger stripe thing showing up when one of the phases is going to be intermediate. So you have a sea of intermediate, then tiger stripe dots in it that are going to be made of mostly intermediate, and then the other stripes are going to be lithium nitrate. So if you get to this point, like if you go through that process and get to here, you got this really complicated morphology. You have little particles in the bottom that are lithium hydroxide. Then you have intermediate phase solid. So the remaining liquid is going to be intermediate phase with droplets in it that are tiger striped intermediate phase and lithium nitrate. Right? I mean,
so we're not going straight down.
No, I mean, you start here and you're cooling straight down, but it's going to follow the phase diagram, right? If you go slow. If you go slow enough, it'll follow the liquidus lines. There's two of them. And then finally get to the eutectic. And in that process, you're forming intermediate phase. So it's got, right? And then you're going to finally have this this eutectic structure, which is this, like,
Then the mole fraction is gonna change.
yeah, because you're right, so like you come out with a 50%, but once you start making lithium, so lithium has to come from somewhere. So the lithium hydroxide is being extracted. It's actually getting lower composition of lithium hydroxide. As you pull out lithium hydroxide, it has to lower the composition. So if all the liquid is down, your composition of the liquid changes, right, until you get to here. And then you're going to have this equilibrium between liquid is still liquid, which is also changing composition, and this intermediate that's a fixed composition. So in both cases, you have a fixed composition of the solid that comes out. So which one is the major phase here depends on the tie line between the liquidus line and this intermediate line. Like which, so that if you have a bigger thing on the right, then you're going to have major liquid phase. The bigger thing on the left, and you have a major, the majority will be the intermediate. I can't tell, it's almost like 50-50. So either one you say is probably okay. But anyway, at some point, the liquid you have remaining will go through a eutectic transition, get this tiger stripe structure. The thing we saw, I showed you pictures of it, I think, but
Okay.
yeah.
So the main summary of this is more or less like that.
Mhm.
We are looking at how
Like something like that.
How fast cooling or slow cooling changes the structure
Yeah,
of the batteries,
right.
and then from there, are there standards? The thing is, are there standards whereby at each phase of cooling, maybe fast cooling or slow cooling, whereby there are defined structures that these things have?
Yeah, I mean crystallographic structures, yeah. Or like domain, like the actual structure gets kinetically determined, right? So you're gonna start, mostly it's like nucleation and growth. So you're gonna have like maybe impurity or something, and then it'll just start growing phases. So usually like spherical domains will grow. The size, so that like you can look at the micrograph and say it's 25% something that's droplets and 75% that's this other thing. So you can see that, you can kind of get it with your eye, ballpark, right? It's not going to be exact because because kinetics determines it somewhat. And then even if you look at what you're doing here, as you're precipitating out the phases, like the composition of the other phase that you form could be like changing. So you could have, in other words, you could have a center of it that's a composition when you hit the liquidus line, but then the composition changes as you go through it. So the composition of the domains you have could be a gradient from the middle to the out, because you as you're forming it, it's going to go on to existing phases. Like it's much easier to nucleate. We'll talk about that later on, but basically homogeneous nucleation that takes like twice the energy of heterogeneous. In other words, if you nucleate on a surface that already is existing, it's half the energy. It's basically, if there's any surface there at all, it'll nucleate on it. So once you form your homogeneous nuclei, or if they form on dirt, then everything else is just going to pile on top, because that's where it's easier for it to nucleate. It only has to make one new surface. Like if you already have a surface, you put atoms on it, you're only making one new surface. If you're starting alone, you have to make 4 new surfaces. Because if you make a cube, there's 6 new surfaces for a cube, right? So it's like 6 times the surface versus adding onto one, just adding. Yeah, actually, you don't make a new surface, you make the sides. So you have a surface nucleate on it. The top isn't made new because you're replacing one with another. Then only the edges of the thing. So it's 4 to 6. Like you have, say it's a square, so you have 4 sides, and a cube would have 2 more. Right, so it's basically 4 to 6 versus isolated homogeneous and a heterogeneous nucleation. So once you have dirt, it's going to nucleate on it because the energy is much lower. And if you calculate it, it ends up being half the energy to nucleate on the surface. So anyway, if you're going through this phase diagram, the particles or the domains you make are going to have a different composition as you go from the center out, because they're depositing along the liquidus line as you cool it, and the composition of the liquid changes as you go through that. So it's kind of complicated, but basically it gives you the ability to say, like, draw a cartoon of what this should look like, and then you look at the micrograph and does it agree or not? If it doesn't agree, then something else is going on, right? Or you have some weird little phase window or something. And also, I mean, with the microscopes, like you can get the diffraction from each of the spots. So you'll see, I think he shows that in here. They do electron diffraction in the microscope, so you can get the crystallographic planes that are interfacing with each other, and you can get the crystallographic sizes. And also he gets atomic, and you can get atomic resolution, so you can measure. See, he measures the lattice sizes here, like these are actual atoms. He's measuring the lattice sizes in these things. So he can, at some point, he says rock, he can tell rock salt from the spinel crystal, which is what the that mixed lithium alloy is, you know. So he can see because it's got a smaller smaller lattice size in the surface somewhere here. I don't know exactly where that micrograph is. It's in the main paper, I guess. This is the supplemental, and this is the paper, right? So let's see. Let me zoom back out here. Like here, see, this is the one. So you can see these are lattice planes. He identifies what planes they are. Actually, from the size, you can tell what, oh, he says 101 plane. Right, so you guys know Miller indices, or anyone not know Miller indices? Speak up now. So basically, these are the, anyway, so it's a 110 plane, and then he's got the 001 plane. So it's like 001 is like a cube, it's just the surface of the cube. And 101 is like a diagonal of the cube. So you intercept the X and the Y, X and the Z planes to get that. So anyway, so those are the planes, and this is rock salt, the 241, and the 485 is the spinel. It labels it here, I guess. The rock salt's NaCl, even though this is LiO, but basically the M's, so they're transition metals, and they can all swap with each other in this. So they're all in that same ionization state. And they're in the rock salt. And then in the M304, it's actually one of them is oxidation 2, and the other's 3, but basically any of the metals, transition metals in this can swap for the 2 positions in the M304 for the spinel structure. So it should be AB204, but basically because it's the transition metals can change their oxidation state, then you get M3 in this thing for the spinel thing. Anyway, so that's kind of the game here. So he's saying, so the weird thing is that like, so this should melt at 191 or 183 would be the eutectic melting point. That's where you're, if you had these lithium hydroxide and lithium nitrate, the lowest point they could melt is 183. But he does this spinning thing at room temperature. So he does this thing at room temperature. So how is it? And he's doing it inside a polypropylene tub, and the tub itself would melt at 166. It would just melt, right? So it'd fall apart and spray things all over the place. Down here at like 166, because over here. So somehow he gets, and the tub never melts. So basically, somehow he's getting this. All right, so I mean, if you believe his scheme, that's what's happening, that these things are melting. Then that because they melt, they can etch into this and break those apart, and then they reform into single crystals and calcinates. That's his whole model. And he says the problem is like, no way can he get to the 183 that he needs, right? Because it's in a plastic tub and it would melt. And it doesn't melt. So, so he comes up with a scheme that, or whoever came up with a scheme, that there's like local heating within the little things inside the thinking, little grains in the thinking mixer. Somehow that local heating allows you to reach the eutectic. That's the theme of this paper. Like somehow, because the heating is local, it doesn't melt the tub that it's in. That's the whole picture of this. And when it can melt, then it's a eutectic liquid. The eutectic liquid can dissolve the rock salt barriers of this and break that thing apart. And then those separate individual single crystals can be calcinated into one big crystal. It's got lower surface area. And also when he's done with that, it's got a smaller interfacial region of rock salt, which means that it's a better cathode. He shows that someplace that the thickness of that interface becomes smaller. There's a TEM micrograph like here. I guess this is one of his SEM. I think this is anyway, this is one of them. It's got a very thin rock salt surface to it. Versus the other one, the original process one has a thicker rock salt surface thing to it. Maybe it's this one. I don't know. Anyway, it ends up, who's measured it in here and reports the size. So that's kind of the whole. There's a processing, it's like a metals processing thing to make cathodes. Yeah, so it isn't, it's kind of interesting to look at, and it takes you down this, how you use these phase diagrams and like, so actually the equilibrium temperatures don't exactly matter here. He's saying he gets this kind of localized heating that's shifting the whole thing, right? So anyway, so let me go through the homework stuff here. So we got this just goes through blah 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 blah, and then which shows a phase. And if you, this is what we were talking about, the 50%, you slow cool 300 to 175. Let me fill this guy up. I think it's important to like get a large version of this somehow, but temperature. Anyway, so it says so it gives, let's see it. So A is let's see, I'm just gonna go through it. So 300 to 175. So it's gonna go. So you're at 50%. So this is this kind of somewhat complicated region. All right, and then, all right, the red ones lead to bad, they don't work. In other words, the red ones don't do this melting and breaking apart of the crystals, and the green ones do. So green are good, red's bad. So he says that the temperature, because of that, and this is 191 or something, that he knows that his temperature range from this mixing process is between like 183 and 192 or something. I think he says that. So he determines what heat he can generate in the Thinky mixer at 6,000 RPM with this particular composition of it. And he says that that could be used by other people to make other things. That's like his gift to the world, but anyway, so we're looking at 300 to 175. So you start at 300, it's gonna melt, and then you're gonna be at 50%, and you go to 175. So this is 150. So 175 is just below 183, right? So it's kind of down in here, right here. Right. So if you do that, you get the intermediate phase. That's it. You're just within the intermediate, right? Cool. Da da da. What about rapid quench from 300 to 100? So if you go, again, you kind of already said this, but so you're at 300, you get down to 100. And then if you do that quickly, then you just separate into pure lithium nitrate and pure lithium hydroxide. So it's completely different. I mean, in one case, you get the one phase, in the other case, you get two phases. It'll be like grains of lithium hydroxide, equal number of grains of lithium nitrate. Take that. So all these are kind of like, oh, so you have to draw a cartoon of that. So the idea is to like make a cartoon. So you have, so the cartoon would look like, let's see, why do I get this thing? When I do this, I get a different answer. And it kind of bothers me a little bit. If you slow cool, right, slow cool. So that was a quench, I said. If you slow cool at 50%, then you do, so if you look slow cool at 50% down to this region here, so you're gonna go to here, and this is gonna make lithium hydroxide. Particles are coming out, and there's a small amount. It's gonna be like, so if you, this amount over the whole thing, it's like 1 or 2%. It's almost nothing. So this stuff, lithium hydroxide would just kind of fall out. And then if you slow cool to here, then you get to this point and your liquid suddenly separates into intermediate and liquid, right? Of those two compositions. And as you go down, there's a lot more intermediate than there is liquid. So it'd be an intermediate phase, and then you get to the eutectic. And then you separate into the eutectic between lithium nitrate and this intermediate. So that's where we get the little drops of tiger stripe thing. That's why I have a picture of that here. So that process would look like if you drew that cartoon of that thing. So you'd have like particles of lithium hydroxide, and then you get a matrix of, then these things are lithium nitrate. And this matrix is that intermediate. Oh no, lithium nitrate tiger stripes. Right, so it's mostly the intermediate and then lithium nitrate. There, sorry, confused, but basically like the A part would look something like that, right? Like, in other words, so that if you look at the micrograph, that's what you should see, right? I mean, that's so there's a point of this is like to say, you start in here, you come down, you make the little particles like 2% lithium hydroxide, then the liquid composition follows this, then you get to that point, and the liquid decomposes into liquid plus the intermediate phase. But as you go down here, there's more, let's see, as you go down here, there's more intermediate phase than there is liquid, so it's an intermediate phase matrix, but it's about like 30% liquid that reaches the eutectic and makes tiger stripes. So the thing should be 30%. This should be 30%. I drew it's about 2%. So it'd be like, actually, these are much bigger. Kind of like that. And then these would be tiger stripe things. They draw it, which are majority intermediate and a little bit of lithium nitrate. So within those little droplets, let's see, within the little droplets at the eutectic, it's about 25%, maybe 20% lithium nitrate and 70% intermediate, right? So you could draw that right too, I guess, if you wanted. So if you blew up one of those droplets, so you're going to have stripes, but so maybe like that, and that's lithium nitrate. This is an intermediate thing, right? So like that. So you can kind of blow up one of those droplets to say what's in it. So that one's pretty complicated, like lithium hydroxide here. Anyway, so you can get the percentages. So it's this is going to be like 20%, right? And then it's kind of at different scales, but basically something like that. So try to get it right. Like it's really important to get the cartoons right. Like when you're thinking about things, I draw a cartoon whenever you're doing stuff, so you can kind of see, to put your thoughts down on paper. So the cartoon might be wrong, but then you can fix it, So if you have a cartoon, you can fix it. If you don't have a cartoon, then you're like just thinking about it and saying things. So the cartoon is the whole game. Drawing a picture of it, because if you have that cartoon, then you can talk about it. You say like, oh, the reason this thing has magnetic properties is because it's within these little domains, that domain does something. But if you don't have the cartoon, you can't put it together. Like it's too complicated. If you just say it, then you won't be able to put together a story that goes with the cartoon. At least that's how I work. I think most people work that way. Like drawing the picture is crucial, and getting the picture right is even more crucial. Because if you draw the picture wrong, then all the stuff you're going to say about it will be wrong too. That was the sizes, the percentages, the compositions, all those things matter, like to get them all right, so that they aren't, otherwise you can't like formulate what's going on, like how, like to predict something from it, right? It's good to have a good cartoon. And also when you try to communicate it to other people, you can see what he does in this paper. The first thing he does is like draw a cartoon of it. He draws whatever that thing is, like his little cartoon of the stuff falling apart. So then you can go back, if you read the paper, and you can start criticizing the cartoon, then you're really criticizing, and it's much easier to criticize a cartoon than his text. Say like, well, that no way does that happen because whatever, they're not hexagons or whatever. So you can kind of attack the cartoon much easier than attacking the text, which is buried in things, so. Anyway, so the cartoons, the details in these kind of pictures, like a picture of what you'd see in a micrograph really matter a lot. Like getting that as exact as you can get it. And using reasoning to draw the picture is really important. So I'm trying to get you to do that in this. So you can kind of start looking at things that way. Like in other words, that's going to be your hypothesis. You know, that cartoon is your hypothesis. So if you have to draw it accurately, like drawing that as accurate as you can from the phase diagram is really important. And if it doesn't agree with your measurements, then you can say like, I have to modify it. I have to modify my thinking about it. You know, so, and then you modify it as you need to. Anyway, a rapid quench 300 to 100 gives you something much simpler, right? So you rapid quench to 100, you get just the two phases. That's just a grain thing. That would just be like 50-50. So that would just be like somehow you draw like a grainy structure. And one of them is going to be one phase, and the other one is going to be the other phase. Not sure how you do it, but that would have to be that same phase. And that one's that one, that one's that one. That's about 50-50. Like it's hydroxide, and then the other one is nitrate. Something like that. And so, I mean, you could do it like a nicer, but as long as you got, as long as you have 50-50, like the size of these, you don't know. Like you don't know how large they are. Basically, it's kinetically determined. So it's going to be the atoms of lithium, what happens when it grows, right? So the atoms of lithium hydroxide, it's a mixture out here, the liquid, and then they have to diffuse over. So there's a diffusion coefficient. Then also, they're going to have to find like nucleation sites. We're going to have to find dirt. So it's going to depend on like how much dirt is in the sample. So you have less dirt, you get larger domains. If you have more dirt, you get smaller domains. If you want to get smaller domains, add dirt. You know, add nucleating sites. Then you get little teeny domains. Right. So you can control that by nucleation. That's a kinetic phenomenon. So you can't, thermodynamics won't predict the size. All the diffusion coefficient and the nucleation are all kinetics, right? So it's going to be 50-50, that's thermodynamics. Basically, it's a mixture of the two to get the cartoon, but you can kind of just say it'll look roughly like this, you know. Let's see. So that's A. If you rapidly cooled at 45%, from 250 to 187, what structures do you expect? So, see, the minute I leave, I forget what it said. So 187, 250 to 187. The 250, 45% is here. So it's right at that green dot. The 187. So this is 183. So it's gonna end up in the middle of this little ditty thing here. Right? I can blow that up somehow. Well, I'm at maximum. I'll do 600. That's why if you take this into a PDF, you can blow it up more. But this is 183, so 180, and this is 191, so 187 is right in the middle of this thing. And it looks like at that point, you're going to get, so this to the left is a little bit smaller than to the right. So you're going to get lithium, you're going to get the intermediate phase as a majority phase, and then a large amount of, so maybe like 40% of the liquid. And then if you just stay there, it just stays liquid of that composition to be about 42% lithium hydroxide in the liquid. If you cool it after that, like if you quench it down, that lithium hydroxide would decompose into the two. The liquid drops would decompose into the two, and they'd be in a matrix of the intermediate phase. Right, so you can kind of get you should be able to kind of get the percentages of everything. If you blow this up more, you could get the 187 exactly, because you know where 183 is. It's a eutectic line. 191 is this liquidus line at that point. So you can kind of scale that to 187. You could figure out exactly what percent of the two. Right. So again, it's like that distance over the whole distance tells you that this phase would be, this phase would be smaller than that. So it'd be these things. Yeah, the large one would be the liquid phase. So it'd be these things precipitating out of that composition, the composition here. should be like 42% liquid. I guess these would precipitate out of the liquid because this is longer than that thing, so it'd be mostly liquid with particles of these falling out. And then it can be confusing. Blowing it up helps a little bit, you know. If you blow it up, you can kind of see, but the liquid line is larger than the solid line. So it's solid precipitating out of liquid. I'm not sure if I said that here. Oh yeah, I did say that. I said that. I wrote down that, kind of jotted down the answers to this, but anyway, so that's that thing. And then and work it out for yourself, because I might say something wrong here, but what about a rapid quench in 250 to 175? So if you take that 45% composition, rapid quenched to what did I say, 175? Rapid quenched at 175. So 175, so 150 is here, 175 is right in the middle of that. So you rapid quench it down to here, then you get mostly, so like, I guess that's about 90% intermediate, then 10% lithium nitrate. That's just little 10% of little spheres, little droplets in the intermediate phase. I get to put 5% here. I mean, you can eyeball it, or you could actually measure it with a ruler if you have one, and figure out what the percentages are. And then the other one is in a rapid quench in 250 to 100. I think that one, 250 for that composition to 100 just gives you the mixture of the two salts. That's going to be 55% of lithium nitrate and 45% lithium hydroxide. So that'll just be the grain thing, like a bunch of grains, but one of them will have bigger grains than the other. One will have 55%, the other one 45. One's just slightly bigger than the other. Yeah.
So for the previous one from 25 dB to 175 dB, how do you know it is 90% lithium nitrate?
Let's see, what is it again? It's 250 to 175.
Yeah.
Yeah, so here, so you're at 250, you're in the melt, and you go to 175, which is, this is 150, so it's kind of like here, right?
Yeah.
So if you rapid quench that, so then the distance from there to here is big, and the distance from here to there is small, right? That means this phase is small, and that phase is big, it's opposites. Anyway, you think you're closer to that, so you're gonna get more of that. But basically, you can tell exactly how much you're gonna get from the distance of that to that over the entire distance. And that'll give you about 90%, I think, by eyeballing it.
Yeah.
But you can measure it with a ruler. And then you know exactly the compositions. It's that composition and that composition. So if you went in with EDEX and measured the composition, lithium, oxygen, whatever, you'd get exactly those two compositions. You know, so you can back up. So you can actually, with the TEM, you can make this phase diagram if you think this way. It helps if you have like a rough idea what it looks like to begin with, but basically you can make the phase diagram with the TEM. You know, I mean, so people do that. All right, so that's B. Then you slow cool the salts at 45 mole fraction from 250 to 100. So you're at 45%, and you're going to do a slow cool down to 100. So you get to this point, and then it's phase separating between liquid and the intermediate phase, and they're about 50-50. Right, so it could precipitate out, or it might make a matrix. You know, so it's kind of like hard to tell what happens. But basically, I think I said it would phase separate out. Let's see, this is 50 slow cool. Yeah, I say it would phase separate out, and then you get a eutectic. Then you have a eutectic decomposition between the intermediate. So it's going to be like 75% intermediate, and then 25% lithium nitrate, and this kind of tiger stripe thing. Then that forms, if you're slow cooling, those are both crystals and they're stuck. And then you basically, that's stuck. Like even when you go to 100, that you still have the tiger stripe domains of these two things, and that phase will precipitate at the bottom of the lithium of the intermediate phase. It's complicated, but basically you're looking at like a tiger stripes eutectic structure from that. Right, so. Then, what's that? So there's a bunch of these to play around with. Then those ABC are playing around with those things. Then he indicates like X doesn't lead to good things, and the red X and the upside down triangle, the green ones do. Then the thing melts at 166. Vessel doesn't melt during mixing. So how does that work? So if you look, so I got this page 484 of this thing. This, let me go back. We got a couple minutes. 484, second column, second paragraph. This is 484. Like here he says 2000 RPM, blah 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 blah, 210, blah blah blah, 190 to so he says the effective temperature is 191 to 202 because he knows, he figures out like where it has to melt. So it doesn't melt at the red and it does melt at the green. So he knows it's somewhere between those two. So the effective temperature he sees is that, which offers insight to blah blah blah. So basically it's just saying that the heat, like these little particles, so they're, I think they're micron size, like 1 micron size, and moving at 6,000 RPM. Somehow they rub against each other and make friction and make heat. They make that heat that allows it to reach this temperature range. Even though it's at room temperature, it reaches 100, 200 degrees C locally, and it melts it, and that's enough to break apart the, do whatever he does in the cartoon. That's his whole thesis. That's his hypothesis. Right. So that's just whether you believe it or not, and then so that's his, to just kind of figure out what he's saying and figure out if you agree with it or not. I can't think of another reason why. That's the only reason I agree with it. But I mean, it doesn't make any sense actually, but you know. Then the spinel. So spinel is normally this AB204. Like you can Google spinel. But I think at Google, it doesn't show the crystallograph, it's rubies of spinel. But basically, he doesn't exactly say like, give the crystallographic shape easily, I don't think. This doesn't, I've been to that Wikipedia page, it doesn't help, and crystal properties don't help. So you can't get the crystallographic picture of this thing anywhere, just the rings and things. Anyway, so basically it's a complicated crystal structure. I can't draw it, you know, but basically it's not really like a rock salt is pretty easy. This is harder. And anyway, it's going to have this 2 different oxidation state metals. It's like the normal way. So it's usually AB2, and A has an oxidation state 2, like calcium, and then B would be 3, like, well, transition metals get to 3. Basically it'd be like some like calcium and transition metals. The transition metals can go 3 or 2, they can change their oxidation state. So basically, it isn't 2 different metals, it's just one metal. It's like M3 because all those metals in this mixture can change their oxidation state, and they could either take a +2 site or a +3 site. That's why. So that's all there is to that. And then there's another question here that's not necessarily related, but when the rock salt, so when they make the nice crystal, they get the thinner layer on the surface. And then I think he explains that on, I wrote down where, page 485, second column at the bottom. 485. I mean, you can read the paper and it might be a better place, but basically, I think somewhere in here he explains about the thickness, like why faster particle that are migrating Oswald ripening fresh. So Oswald ripening means like the little fish are eaten by the big fish. So you have domains, small domains, big domains. The big domains will grow by eating up the small domains, which have more surface area. That's Oswald ripening, right? So like as you calcinate these things, that kind of process is going on. The little ones are being eaten by the big ones. It's basically you're growing these large crystals by that kind of process. I'll talk about Oswald ripening later on, but It's a kinetic thing too, it isn't thermal, but basically we'll talk about it. Anyway, so he says something about Oswald ripening, you can Google it too. Indicate less, supplementary, blah, 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 it's further supported by blah, blah, blah. Same trend can be observed, he just says it happens, I think. I mean, you can, I think it's in this part, he talks about the thickness of that layer and why it's better in his lithium hydroxide, lithium nitrate mixture. The thinner layer is better because it doesn't, that's the part that's depleting, it interferes with the transport of lithium into the spinel crystal. And it also consumes the lithium and doesn't release it. So it's like depleting. So you put so much lithium in your battery, you want to use it for power, but you can't because it's stuck in the rock salt. And then also it's a barrier for the lithium to get into the part that's going to release it and take it to make the battery work. So this is it's a good thing to make that thinner. That might be more important than the business about making big crystals. He has a thinner surface layer. So anyway, that's about it. So hopefully you can learn something about batteries by fishing through this thing. And the phase diagram is almost incidental, but it's kind of like give you a feel for how you do it. Like you're doing TEM microscopy and like sorting out phases and things. It's useful to kind of be able to use the phase diagrams. So that's about it. We're out of time. But any other questions or anything? That's about it. So mostly like this kind of thing is the normal materials thermal class. It's just all phase diagrams, but and not everyone's going to run a TEM. Like if you do polymers, then this is of no use to you at all. Put it that way, but it might be good to know about it, I guess. But basically, you never know what you're going to do. Like we have some stuff going on with batteries, lithium with the anode though, not the cathode, but so you do run into stuff. Like I'm a polymer person, so you do different things, so eventually you might run into where you need this stuff. But anyway, that's about it. So email me if you got like there's problems with it, and